Okay, good morning, ladies and gentlemen. I will introduce very quickly our institute. Then I will talk about my chair and then give the word to my colleagues. So, Institute for Geotechnics was established in 1935. Professor Robert Heffley was one of its founders. And currently it has 4 chairs. Untertagbau of Professor Anagnostou, Geotechnik of Professor Anastasopoulos, and Geomechanics and Grundbau, which is my chair. We also have a new chair, if you don't know, for Alpine Mass Movements of Professor John Gom. This is in collaboration with SLF in Davos. Environmental Geotechnics and Clay Lab is an independent group of Dr. Michael Plotze. And Transportational Geotechnics is the group of Dr. Hauswirth. I will move to Research and Innovation in Geomechanics group. And I have to confess that I was really lucky in the past 10 years being exposed to some very interesting real-life problems, such as Bratas landslide and the Leaning Tower of St. Moritz, underwater landslides in the Caspian Sea and Swiss lakes, reactivated landslides by excavation in Mexico and Switzerland, earthquake-triggered delayed snow avalanches in Italy and India, tailings dam collapses in Israel and Brazil, and finally, tsunamis caused by gold mine tailings collapse in Papua New Guinea. So I will take you briefly through these projects. Our work to understand the behavior of the Bratas landslide and the Leaning Tower of St. Moritz was published in nice journals and even got an award. But to tell you the truth, I'm not sure that we still understand what's going on there. In 2012, I was asked by BP to help them to explain enormous landslides at the bottom of the Caspian Sea and to help them to find the safe place for their new gas platform. And to do that, we developed a novel shear bend propagation approach to the slope stability, which we also apply in Swiss lakes, where I don't know if you know this, in 1601 there was an earthquake in Lake Lucerne, which caused a tsunami wave, a 3-meter high. It caused a landslide, and the landslide caused a tsunami wave, which was 3-meter high and destroyed the downtown of Lucerne. But even more important, for me at least, only after 5 minutes it reached this place and destroyed the port here. And why is it important? Because now I have my boat, little boat there. In 2010 and 2013, I was asked by Allianz insurance company to investigate some landslides in Mexico along a new highway between the Mexico City and the Gulf of Mexico. This part of the highway goes through beautiful mountains, Sierra Madre Oriental. I wanted to show you a picture, but unfortunately I couldn't find a picture where I am not there, so please forgive me. And one of the landslides was very interesting there. They excavated for the highway almost 50 meters below the existing landslide, in the stable ground. And still they managed to reactivate it. A similar problem I encountered a bit later in 2017 in Zurich, actually, on the Zurichberg. Sorry. where there was a new project which they tried to excavate below an existing landslide which took place in 1979 and damaged some buildings around this. And the question is, and again, you know, the excavation is not at the bottom of the landslide. It's actually away from the landslide. But how do you excavate safely that you do not reactivate it? So this was related to the so-called landslide influence zone, which we had to develop a novel approach for excavation there and design. This Rigapiana avalanche in 2017 in Italy, it was devastating. It destroyed a hotel and killed 29 people. And what is interesting about this avalanche that it took place 40 minutes after an earthquake. Earthquake only 40 kilometers away. And there was a big debate whether it is just a delayed effect of the earthquake or not. And when we started to investigate it, we discovered two similar avalanches in Himalayas, in India, which destroyed some military equipment and also took place after the earthquake, around 40 minutes after the earthquake. And to explain this, we had to propose the mechanism of delayed release in earthquake-induced avalanches, which was published in the Proceedings of the Royal Society. 2017, a phosphorus gypsum stack collapsed in Israel, resulting in a tsunami wave of polluted water, which traveled 20 kilometers through a nature reserve, killing everything on its way. And to explain this mechanism, what happened there, we had to develop piping criteria for hydraulically stable and isotropic slopes. If you think it is an easy problem to solve, then I have to tell you Karl Terzaghi had a different opinion in 1948. Another interesting case study is the tailings dam collapse in Brumadinho in Brazil in 2019. It killed 270 people, and it took everyone by surprise because it took place 3 years after the dam was closed. And normally we know after the dam is closed, due to consolidation, material just becomes stronger. You do not expect a collapse after the closure. So by carefully modeling the entire dam evolution from the initial construction to operation, closing and post-closing behavior and collapse, we discovered that the mechanism is quite interesting actually. It's a slow growth of slip surfaces driven by the creep in the tailings material. And what is really scary is that you do not have any warning. You do not, normally people monitor displacements. There were no large displacements before the collapse. It just went like that. And this is a problem because after this collapse, in Brazil, they will be closing a lot of dams like that. But apparently, this is not the end of the story, right, when you close the dam. You need to be very careful. By the way, a paper on this is going to come out in one of the Nature Portfolio journals next week, probably. So if you're interested in details, just Google it. And to finish this part of my talk, I'm going to tell you a tragic comic story of the gold mine in Papua New Guinea, which was excavated by the Newcrest Australian mining company. So they were dumping tailings in the ocean because there is a pretty steep continental slope there, and they hope that the tailings will just roll down and disappear somewhere in the depth. What happened, the tailings did not roll down. They accumulated on the slope until it was 100 meters thick, and then they collapsed, creating a tsunami wave which destroyed the boats in their harbor here. And our task was to develop a safe approach for deposition of the tailings in the ocean. Of course, as you have already seen, these solutions required development of some novel numerical, experimental, and analytical approaches. And this required some innovation in numerical modeling, application of novel sensor technologies in the field and in the laboratory. And then we're also trying to share these novel approaches in teaching, in technology transfer, and even trying to solve some old mysteries, as I'm going to show to you soon. Some examples of innovation in numerical modeling you can see here. One is large deformation finite element analysis for a landslide evolution. Then we have an in-house developed material point method. Mark Kohler is here, which we use for seismic landslide analysis, large deformation landslide analysis. And one of the speakers here today, David Pirozzi, also developed a discrete element method, which we use to understand better soil behavior and apply this knowledge in solution of geotechnical boundary value problems, such as this soil wall interaction for a project which was supported by Astra. You will hear more about it. We try to take advantage of the ongoing revolution in the sensor technologies by applying them to geotechnical monitoring, like in investigation of a landslide on a flank of Lago di Luzzone. This landslide, people are afraid, is that one day it will accelerate, in particular because of seismic loading, and fall into the lake, causing a tsunami wave, similar to the Vajont disaster. This project was carried out by Mark Kohler, and we used here fiber optic sensors for landslide, monitoring landslide displacements together with conventional technique. The project was funded by Swiss Federal Office of Energy. It's actually Dr. Hauswirth who will lead the excursion today, who is our expert on fiber optic sensing. And he's using it also to understand better behavior of asphalts, like in this Astra-sponsored project in Zurich Airport. But also, by placing the sensor secretly in the ground, you can use it for object identification and intrusion detection. And we got a patent for this method. Another patent we got for a novel device, inclinator deformator, for measuring earth pressures in the landslides. We also try to innovate in laboratory experiments using sensors. We instrumented a chute with fiber optics, and we were the first group to prove propagation of slip surfaces in the slopes. We actually managed to measure them physically. Also, in David Pirozzi project, fiber optic helped us to instrument the setup for soil structure interaction in stem walls. And our pride is the new ring shear device built by Mark Kohler in collaboration with many, many people. And here we can study behavior of soil in the slip surface of the landslide in a very broad range of velocities, also measuring excess pore water pressures and temperatures. We try to share our innovation with our students, both in undergraduate courses, Grundbau, and in the graduate courses, constitutive and numerical modeling. And there is a special graduate course, master course in forensic geotechnical engineering, which is completely devoted to investigation of geotechnical failures and case studies. And students used to like it. 10 years ago, we got this golden all, but now, after COVID, nobody comes to the class anymore. I think it's actually not my sole experience, right? So we also try to share this innovation with industry via the patents that I have mentioned. 12 years ago already, I think, my ex-PhD students founded a company, Marmota, which won a national venture competition for the best business idea, and you can see we got this fat check as a prize. But the most important thing is that they are still alive and keep providing fiber optic sensing solution all over the world, like in this Guinness record foundation load testing in Dubai Creek Tower, the next tallest tower in the world, probably like for half a month, right, until they build the next tallest tower. So, my friends, this would be a good point to finish, but before I finish, I need to warn you, because, you may try to use this innovation for solving some old Soviet mysteries. And this is dangerous because you may end up in a comic strip, as you can see, me and Professor Gom here, being casted in Swiss TV as a James Bond villain. And not only National Geographic, the New York Times, and the New Yorker are going to chase you for an interview, but also 20 Minuten. And then all your ex-girlfriends are going to call you, and your wife is not going to be amused. But this is a different story, so at this stage I would like to thank you for your kind attention and pass the word to my colleague, Professor Anastasopoulos.